right, welcome to the deep dive. Today, we're plunging into a topic that really stretches the imagination. We're looking at the profound, sometimes pretty mind-bending intersection of consciousness, the philosophy of mind, and, well, the fundamental principles of quantum mechanics.
Quite a mix.
It is. We're basically on a journey to understand how our very minds might connect somehow to the deepest fabric of reality itself.
Yeah.
And our mission today is pretty simple. We want to unpack these really complex ideas, help you distinguish, the common myths from what the science actually points towards, and explore some of the biggest unanswered questions out there right at the frontier of physics and philosophy. The goal is for you to walk away with a kind of shortcut to being genuinely well-informed on this fascinating subject, maybe pick up some surprising facts too.
Absolutely. And our deep dive today, it's drawing heavily from an analysis of a YouTube discussion. The title was something like, "Is there a connection between philosophy of mind and quantum mechanics?" And this discussion, it provides a really curated look at some foundational theoretical physics. It weaves in historical thought experiments to explore these, well, let's face it, elusive connections.
Okay, so let's kick things off with the really big question, the one that anchors this whole thing. Is there a legitimate link between the philosophy of mind, specifically consciousness, and quantum mechanics? I mean, it sounds almost like science fiction, right?
It does, but it's a question that has genuinely captivated some brilliant minds in physics for decades.
Yeah.
It's actually remarkable how far back this line of thinking goes. Our sources really highlight the physicist Eugene Wigner. He delved into this back in the early 1960s in a paper called On the Mind-Body Question. And Wigner introduced this famous thought experiment. It was designed to grapple with what physicists call the measurement problem in quantum mechanics.
Ah, the measurement problem. That big, perplexing question of how and when a quantum wave function collapses, going from all those possibilities down to just one definite outcome.
Exactly. That's the core of it. How does that happen?
And it's fascinating. Like you said, Wigner's experiment is famous, but the sources note it actually appeared even earlier.
That's right. It first surfaced in Hugh Everett's extended thesis from 1956.
Everett. Okay, yeah, he's absolutely pivotal here. The many worlds guy.
The many worlds guy, indeed. Hugh Everett, the architect of the many worlds interpretation, or MWI. And his idea is, well, truly mind-bending. He proposed that all possible outcomes of a quantum measurement actually happen.
All of them.
All of them. But, and this is the crucial part, they happen in separate, non-communicating branches of reality. The universe constantly splits, according to Everett.
Okay, wow. If you start trying to connect that to your own experience,
Yeah.
the philosophical implications are huge.
They're profound. If the universe is constantly branching, what happens to your consciousness? I mean, are you copied into every single one of those branches?
Are there infinite versions of me?
That's the question it forces you to ask. It really pushes us into deep, deep territory about metaphysics, identity, what it even means to be you.
Right. Okay, let's pause there and unpack something else crucial because it relates to this branching and collapsing, the wave function itself. Our sources point out a really common misunderstanding here. When people hear wave function, they often picture, a literal physical wave, like ripples on water, or maybe an electromagnetic wave, something moving through our normal 3D space describing where a particle is. It feels intuitive.
It feels intuitive, but it's fundamentally misleading. And that popular picture, it just completely breaks down when you look closer. The critical clarification here is this. The wave function isn't a physical thing waving in our space. It's a mathematical object, a tool.
A mathematical object, so what does it do?
What it does is it assigns complex numbers. That's just a type of number mathematicians use to all possible configurations of a quantum system. Think about it like this. For just one particle, okay, maybe you can kind of map its wave function onto 3D space. Fine. But as soon as you have two particles, the wave function describing both of them exists in a six-dimensional configuration space.
6 dimensions, not 3.
6. And for 3 particles, it's a 9-dimensional space. For 10 particles, you're talking a 30-dimensional space.
Okay, my head's starting to spin with the dimensions.
Yeah, the exact numbers aren't the main point. The crucial thing to grasp is that the wave function doesn't live in our familiar physical reality. It lives in this abstract, multi-dimensional configuration space, a space of possibilities.
So that whole image, the metaphor of waves moving through space, it doesn't hold up. It's a simplification that can lead you astray.
Precisely. It breaks down very quickly.
And understanding its abstract nature, makes Wigner's original speculation even more, well, intriguing. His idea that consciousness itself might be the trigger, the thing that collapses the wave function.
Right. He was suggesting quite radically, that the act of observation by a conscious observer might play a fundamental role in making reality definite. And this sets up this fascinating, almost circular loop, doesn't it?
How so?
Well, on one side, you have Wigner's thought, consciousness affects quantum systems? Maybe. But on the other side, we know quantum systems are what make up our brains, which is presumably where consciousness arises from.
Ah, I see. So consciousness affects quantum mechanics, and quantum mechanics underlies consciousness. It's a loop.
Exactly. And our sources emphasize that this leads to two really fundamental questions that are still very much open. They're not solved.
Yeah.
First, what actually causes measurement outcomes to become definite? What picks one result? And second, is consciousness necessary for that? Do you need a conscious observer for physical outcomes to become fixed?
And the point is, these aren't just philosophical musings anymore. They're seen as real, meaningful, scientific questions, even if we don't have the answers yet.
Correct. They remain active areas of inquiry.
Okay, so let's push the abstraction even further for a moment to really get a sense of how weird this quantum world is. The sources briefly mention the mathematical homes of these wave functions, Hilbert spaces.
Right, Hilbert spaces. These are the abstract mathematical environments where wave functions, mathematically speaking, live. And what's really thought-provoking here is an analogy the sources draw. It's a bit technical, but stick with me. They suggest that Hilbert spaces, a bit like something called gauge symmetries in other parts of physics, might be mathematically, well, redundant.
Redundant, meaning they have extra information.
Kind of. It means they might contain more mathematical structure, more information that is strictly needed to describe the physical reality we observe. Think of it like having a map with way too many grid lines. Some of those lines might just be different ways of labeling the same place, not pointing to physically different locations.
Okay, so what's the implication of that?
The implication is potentially profound. It suggests that a significant chunk of quantum theory's mathematical machinery might be epistemological.
Epistemological, meaning about how we know things.
Exactly. Tools for knowing, for describing, for predicting, rather than being purely ontological.
Ontological, describing what actually exists, fundamentally.
Right. So maybe some of the complex math and quantum mechanics is more about our framework for understanding reality, rather than a direct picture of that reality itself. Our description versus the thing described. That's a big shift.
That is a huge shift in perspective. Wow. It helps, maybe, to get some historical grounding, to remember where quantum theory even came from. It wasn't dreamed up out of pure philosophy, right?
Not at all. It started with a very real, very concrete experimental problem back in the late 19th century, the black body radiation problem.
Black body radiation. That's the weird glow from heated objects in cavities.
That's the one. Experimentalists were measuring the spectrum of light, the colors, coming from these heated cavities, and they got this specific curve. And the problem was, the physics of the time, classical physics, completely failed to predict that curve. It gave nonsensical answers, like infinite energy at high frequencies, the ultraviolet catastrophe.
So classical physics was broken.
Fundamentally broken for this problem. And it was Max Planck who finally cracked it. Around 1900, he managed to derive a formula that perfectly matched the experimental curve. But to do it, he had to make a really radical assumption. He had to assume energy wasn't continuous.
Ah, this is where the quanta come in.
This is exactly where quanta come in. He proposed that energy is emitted and absorbed in discrete packets, or quanta. The size of these packets depended on the frequency of the light, and a new fundamental constant he introduced, Planck's constant.
And the amazing detail our sources mention is that Planck didn't even fully believe it himself at first.
That's the incredible part. His original intention, apparently, was just to use H as a kind of mathematical trick, a fudge factor to make the sums work out. He planned to eventually make H go to zero in his final theory.
But he couldn't.
He couldn't. Nature didn't let him. The constant H had to have a specific non-zero value to match reality. The universe, it turned out, is fundamentally quantized. Energy comes in chunks. It wasn't just a trick.
Mind-blowing. He stumbled upon a fundamental truth about the universe almost by accident.
In a way, yes. He opened the door to the entire quantum revolution.
Okay, so let's try and pull these threads together. We've covered a lot of ground, Wigner, Everett, wave functions, consciousness, Hilbert spaces, Planck. What are the key takeaways for you, the listener, trying to make sense of this wild and wonderful quantum world?
I think the first big one, and the sources stress this, is that the wave function. It's not a thing moving around in space like we imagine waves. It's fundamentally a mathematical tool. An abstract object that lives in configuration space, designed purely to help us predict the outcomes of experiments. We have to resist that intuitive but wrong physical picture.
Right. Get rid of the image of little waves rippling through our room. It's math. Okay, takeaway number 2.
The second is about consciousness. That speculative idea, tracing back to Wigner and others, that consciousness might be somehow involved in measurement outcomes. Look, it's definitely not a proven fact. It's highly speculative. But it's not dismissed out of hand either. It remains a meaningful, active frontier of thought in both physics and philosophy. The question is still on the table.
So it's okay to think about it, but don't assume science has proven consciousness collapses anything.
Precisely. Keep it in the realm of fascinating, open questions.
And the third big point.
I think the third point is about achieving a more, let's say, mature understanding of quantum mechanics. It means moving beyond those simple, often misleading pictures you get in introductory explanations. It involves appreciating that the picture of reality Hugh gives us is deeply mathematical, incredibly abstract, and frankly, metaphysically ambiguous. It doesn't give easy answers about what reality is.
So the sources are really inviting us to be careful with our metaphors in physics.
Very careful. Recognize the limits of our current theories. Don't overinterpret the math, and appreciate the profound philosophical questions that are actually baked into our most successful scientific models. They're not separate things.
It's really a journey to the absolute edge of what we currently understand, isn't it? About reality itself. We've explored these really fascinating, still unanswered questions, right where physics meets philosophy, hopefully helping you see past some common myths and grasp these incredibly nuanced ideas.
And maybe it leaves you with a deeper thought to ponder. Building on that idea of epistemology versus ontology. If some of our most fundamental scientific tools, like the wave function, are potentially more about how we know reality, how we describe and predict it, rather than being a direct map of what truly exists, well, what does that tell us about the ultimate nature of reality itself? And maybe about our own place within it.
That is definitely something to mull over, a really provocative thought to end on. Absolutely. And if this deep dive has sparked your curiosity, please explore these concepts further. You could look into Everett's many worlds interpretation in more detail, or read about the ongoing debates surrounding the measurement problem. There's a whole universe of thought out there. Thanks so much for joining us on The Deep Dive.